Welcome. This is the third video in our Newtonian motion practical. So we're going to have a look at this graph that we made, and we're going to analyze it a bit further. So in our theory, get the right picture. There we go. Our hypothesis was that time squared would be proportional to 1 on m1, and our graph. We don't have the evidence for that. We'll come to the conclusion in a minute. We're going to do a few things with the data, well, with this graph at least. Okay, so I've written down some notes ahead of time, so this doesn't take a great deal of time. So graph is linear, so straight line. It's non-proportional because it doesn't go close to the origin, let alone through it. And it's a weak correlation. Now, if you're not familiar with correlation, let's see if I find my notes. Yep. Okay, so R squared is a measure of correlation. I think it's a coefficient determination. It's a scale that goes from 0 to 1. We're not going to go through the mathematics how it's derived. We're just getting it off the graph. Now, basically, 1 would be a perfect correlation. So something like that, like all the data is on the linear line. So you see 0.99, you have something that looks like a pretty good line. 0.083, you get something that's a bit more scattered, but it's very obvious there's a trend upwards. And 0.37 is a bit of a mess, but you can see, okay, there's not much near the top here. There's stuff at the top. There's more at the bottom on the left-hand side. There is a general upward trend, but as a weak correlation. And ours is a weak correlation, which was surprising because physics experiments usually do better than that. You can usually get, even with kind of a bit lackadaisical physics prac, with a reasonable technique done quickly, you might get a correlation of 0.8, 0.85, and if you really take your time and you get lots of data and you do it really well, you can get 0.95. So physics is blessed the fact that we can actually get very good correlations generally, but this was pretty poor because I left a lot of freedom in terms of the technique, and we'll come to that in a minute. All right, the gradient of the graph. Now we're going to go back here. So now I use a linear equation in my graph. So the linear equation equals y, which is t squared, equals slope 0.11 times x, which is 1 on m1, and we'll ignore the y-intercept for now. So the slope is 0.11. I'm not going to bother with any more significant figures than that because, well, there's not particularly good data at this point anyway. So if you use a graphics calculator, you can get a better a number of significant figures for the slope, but this will be us for now. Okay, now the units, in a pinch, if you're not sure what the units are, take your y units, divide by your x units. Now, actually, because your x units is inverse kilograms, that would be seconds times kilograms. There you go. Seconds kilograms. Oh, sorry, seconds squared kilograms. Yeah, so I'm dividing something that's already inverted. So thereby dividing. So seconds squared kilograms is the unit for the slope. Okay. Considering the slope from this, so even though we didn't get proportionality, we might actually still be able to use this to determine g. Now we know what s is. We know what the mt is. We know what the total mass. In the case of this experiment, we go up. I think I wrote it down somewhere. Let's go up. Yes. Distance traveled was 0.6 meters and total mass was 1 kilogram. I think I wrote that down, so that's fine. All right. So we got the gradients. So we're actually going to rearrange this equation. So this says, and the way I've orientated this, dependent variable equals bunch of constants, that's going to be our slope, times by independent variable, y equals slope times x. There's a plus c, but we'll ignore it. And we're going to determine what g is from this, because I know what this number is according to my graph, that's 0.11, but I can rearrange this and solve for g. So if slope equals 2s mass total divided by g, then g equals 2s mass total divided by slope. So all I've done is times g across and divide the slope across. So let's write that out. So 2 times 0.6 times 1.0 divided by 0.11. Let's see how horrible this is. All right, so my calculator here. 2 times 0.6 times 1, that's redundant, divided by 0.11. I get a gravitational acceleration of 10.9. I'll just round it there. There's no particularly, this was a 2-cent figure, so probably I'd round that to, actually, if I was consistent, I'd round that to 11 meters per second squared. Okay, that is my gravitational acceleration according to this, at least in the order of magnitude. Let's go calculate the percentage error. And bear with me, I'm actually going to have to write this up. Percentage error. Okay, so we're going to write this as G experimental minus kind of G actual or G theoretical. Okay. All right. Now, okay. That's close bracket. Divided by G theoretical. And then we're going to times all of that by, so times by 100%. Okay, so I'm just going to write this out here. All right, and you can watch me do this, so I don't need to necessarily write it all out like that. So you can watch in the calculator. So I'll take this 0.9 minus 9.8, okay, equals, divided by 9.8. Oopsie, that's 98, so maybe I'll times by 10 to fix that. There we go. And then I'm going to times by 100. I'm going to just times by 10 before. All right, there we go. So the error is 11.2%. Meh, it's not great, but it's not horrible. At least you've gotten something in the ballpark. So there you go. You've actually got an estimated G. That's pretty cool. We'll show you another way in a different experiment, a one that's kind of a little bit more foolproof. Another way of doing this, and you're probably going to get a better percentage error. I managed to teach grade 2s a way to actually measure G. Well, I did a lot of kind of spreadsheets where all they had to do was type in numbers and graphs were automatically done for them. But all the same, if they can get measures of G better than 11% error, you can too. Okay, conclusion. A graph of t-squared versus inverse mass. One was a weak linear correlation that did not pass through the origin. The hypothesis of t-squared is proportional to 1 on m could not be supported. So I'm not saying it's not true, just the evidence that isn't there. It's not strong enough. Errors. Random errors evidence from a poor precision of data. Let me take up the picture so we understand what we mean by accuracy and precision. That one. Correlation. So that's a nice picture. We'll come back to parallax error in a minute. There we go. Okay, so the little targets is a little reminder. So when we're looking at this, we can see that there's a lot of distance between the graph and the data. The line of this fit in the data. And that's a result of having poor precision. So your bullets kind of scatter around the place. In fact, ours is actually in this category, not accurate and not precise, but we'll focus on the precision. Now we're going to break up our errors. The method needs to be improved to reduce the effect of human reaction time. Yeah, so basically your values were not consistent. You can see it in the data as well. There's a lot of jumping around. The repeating and averaging does help that a bit. So, like for example, 6.68, 0.76, 0.74. That one seems like an outlier. A second one was probably the most extreme. Although these actually maybe they're a little bit more consistent, but this point is like way out there. Actually, these aren't in. This order gets reversed, so actually that is the second one. All right, and you can see there's a big fluctuation in this data anyway. It's a big fluctuation in terms of where these points are in terms of the line of best fit. So that demonstrates bad precision. So, excuse me, precision. Sorry, random error. So we need to improve the method. So I mentioned a bit when I was observing the method of students doing this one. They were doing they were giving the instructions to each other in terms of the timing. So they might count down and say start, and then that someone verbally tells the person the stopwatch to start, and then they catch at the end and say stop. That's the main reason why we had as many errors as we did. Random error and particularly systematic error, and I'll explain why in a minute. So that technique needs to be improved. You could use the same equipment and improve it. The idea is you'd have you might count down. You have the person in the stopwatch would be at the end where the car is about to go past, and the person who's let it go could count down 3, 2, 1, and just simultaneously presses the start as they release it. So 0, the simultaneous release of the car as the other student presses the stopwatch, and then that person watches until it goes to the end. So they don't have to tell. No one has to tell the person the stopwatch to stop the stopwatch because they're observing it, and they'll stop the stopwatch as they line up and watch the car go past. But in the technique I observed, someone was calling up to the person the stopwatch, telling them to start and stop. That the human reaction time of that is what's going to affect the random error. So you try trying to click a stopwatch and try to see what your reaction time is. There's a limitation and there's fluctuation. Okay, you could actually improve this a little bit more by taking more measurements, but I imagine the method itself was the major effect. Systematic error. So if we assumed that my hypothesis was true, there's a proportional graph. The graph shouldn't be going up that way. It should be, the slope was just a little bit steeper than, actually I would have to double check that. I would have to look at the rearrangement of the equation, but the slope's not quite right, but it's approximately correct. The graph should be going through or close to 0, 0 and going up here through there. So if you drew a parallel line through there, that would be better. That would actually demonstrate very high accuracy if you had that, because it's doing essentially what we suspected it should be doing. But I said may because in my experiment I had a theory and I tested that theory, and it's either the error made the theory wrong or the theory is wrong, so I said may. The systematic error may be evidence from the poor accuracy of the data. The graphs did not pass through the origin, and t-squared values were in general higher than they should be from the equation. But everything's been shifted up. So the main reason for this, I believe, is calling out start stop. So whenever you call out to someone with a timer, start the timer, or just say start, they've got to hear that, they have to react, and they have then the mechanical movement of your finger. You're adding extra time when you do that, and also with stop. So you're adding extra time. Might be half a second, might be just a few milliseconds, but it's shifting the time up. So I think that's the main reason why we have so much systematic error. There's also another form of error that I'll make mention, parallax error. So parallax error is when you're not observing something in a straight line. I would have to think about, because it might have been the case of the person who was observing the car go past and called out stop was looking at that in line with where it was. But it was just poor technique in general. Even so, that would add to systematic error. What you wanted was the person with the stopwatch to watch at the point at which the cut would have gone past the 0.6 meter mark, and as that goes past, they would have clicked stop. Okay. So those are the discussion of errors. Now, I just summarized that very quickly. There's probably one more thing I put into systematic error, and I might mention there was assumption. That friction could be ignored. All right, now without any stuff ups in the experiment, if you did the experiment perfectly, chances are you would actually get a greater t-squared anyway, because this is a mechanical. The cut, it's got moving parts and it has to overcome static friction, and there's friction throughout the pulley and whatnot. So friction, I should say. There we go. That's better. All right. Okay, and I should say this will also add to the time values. Yeah, so the idea in reality that friction would increase the time. Maybe it's negligible, maybe it's substantive. If we had better technique and we kind of eliminated all the other factors, you could probably see how much friction. But chances are the friction itself will make the time values higher than they would be otherwise, because in a frictionless track, well, then you know you've eliminated that factor. But with the moving parts, that's going to cause drag forces, and there's going to be some degree of increase in time as a result of the friction. So I've had that point as well. Okay, now in your discussion, you should also be talking about improvements. Now, why don't we just have a quick gander at some ideas for this? So I went and had a look at Google Images for different techniques. So let's have a look at, I think we said Newton's second law. Cart, weight, practical. Okay. So let's have a look at some images and see other ways to set it up. Okay. Now, you've got some images. They're talking about smart pulley, clamp, cart. Okay, looks like this. You can actually there's a couple of ways you can improve upon this. I'm not finding the images I'm looking for. One is, okay, you have electronic devices that kind of eliminates the human factor, and you analyze basically when they go through certain devices. So this, I think this pulley here in that image there, this pulley, it records how fast it's moving, and thereby, or maybe even how much distance is traveled in a set amount of time, and then it can actually relay that information. I believe that's actually a light gate as well that reports when something's passing through it. There's a few ways that you configure this better. I saw some better images last time I did this though. Okay, another one, you could eliminate friction by using something. Let's go. Yeah, so this is an little air track, and I believe, and that's kind of like the device kind of hovers on there. You more or less eliminated friction from that, so you can ignore friction in that case if you use an air track. So here's another example. So these are like little gliders. Where are we? I should just go back to that. They've got also the different experiments going on. So we could have used these little air gliders on the track. these essentially just slide past, slide over with minimal friction. Excuse me. So there's a number of ways we can do this. We can eliminate improved techniques. So there are devices that significantly reduce friction. Such as the air tracks. And eliminates human reaction time. So that would be like data logging equipment, light gates, and smart pulleys. Not sure if the smart pulleys might actually add to the friction, considering they are measuring, but I'm sure what I mean by a light gate. I might just search for that itself. All right, let's find a picture of it in use. Excuse me. All right, I'll use any of these essentially. Okay, so for example, you just have a trolley going down a slope. Okay, it passes by light gate 1 and light gate 2. So you have set up these 2 light gates, and you have a little thing here, like a little card. So it sends a signal. There's actually a little laser that goes, it's shaped like a little U, like these. And the little card goes through that little hole, that little space here. So they're hanging up like that. And it blocks the laser. So then if it blocks the laser, it sends a signal. So you can look at the start of when it goes through light gate 1 and then light gate 2. Now, if you've already measured the distance between light gate 1 and light gate 2, you'll look at the delay in time between when the laser is blocked in light gate 1 and light gate 2, and from that you can determine velocity. So that is one way you can measure velocity. And then we could approach the experiment somewhat differently as well. So that's how you essentially how you can use light gates. If you use actually 2 pairs, you can actually measure acceleration as well. So you have like 1 pair close together to measure 1 speed, and then another pair not too far away, again close together to measure the other speed. And then you can work out essentially the average acceleration between those points. So light gates are kind of nifty, but we didn't use them for this experiment. So because I actually wanted to make this kind of cheap and nasty, so we'd actually make a point about errors and explain the fact that, yeah, we need to reduce errors in future. Now, I'll make one more point. If you're struggling to find an answer of things to do to reduce errors, you can always say repeat an average to reduce random errors. So just keep measuring the same thing and average it out. Generally helps. And in terms of reducing systematic error, calibration of measurement devices. So that's like resetting your weight scale back to 0, making sure your ruler it starts from 0, things of that nature. Just calibrate your devices, and that generally tends to help. Okay, extensions. If you have a look around, there's other ways to do the experiment, not just in terms of reducing error. That's the improvements. Extensions. When I looked around at Newton's so I found some other ways to go at doing this. Maybe if we have a look at some of these images. Well, what could you do? We've talked about the light gate. That's a light gate there. I saw some pictures where they actually had they were doing it. They had basically something like this. They had an experiment where they were doing it with a ramp, and so they had a ramp, and then you had this free hanging weight. You could do that. You could actually change the angle of the ramp and then measure the acceleration that way. So then you have like the ramp effect as well as the weight effect going on there. That's another way you can approach the problem. And in this case, it looks like they've got kind of like two pulleys going on here, pulling both ways. So you could actually determine from that. You could probably do, you can do more different kinds of experiments in relation to this. Another way, ticket timer is an old-fashioned way of doing it. It does introduce more friction into there, but that's another approach. It doesn't necessarily help with the friction though. Okay, so that is all I'm really going to do in relation to this experiment. So I hope that was kind of thought-provoking, and now you kind of know how to go about doing a data analysis. This was quite rushed, but you can expand upon this detail in your own experiments in the future. All right, so signing off.